Hello, everyone. Today, I'd like to introduce Lee Sidebottom. He's the Director of Concept Applications at NeuroTracker. NeuroTracker is a company using neurotechnology to focus on the human performance and wellness space. They are partnered with the Faubert Lab at the University of Montreal. He holds a master's degree from the University of Central Lancashire. So Lee, can you tell us your story? I'd love to hear a bit more.
Yeah, sure. I'm pleased to be on this exciting space to be working in, and it's great to see a podcast starting up here. So yeah, it's a little bit random, my story. So I used to do I worked for NeuroTracker, which is a tech transfer company. So we basically take scientific breakthroughs in a lab and commercialize them. So we've got 3 so far. We've only fully commercialized 1, but we have others in development. So yeah, we began 14 years ago. And actually, it was a little bit strange because it was a case of there being a market need for something that didn't exist and going out to find it. So I did some consultancy work with Manchester United Football Club because I'm from Manchester, and it was only occasional. And then I was traveling at one point, and then I got a phone call from one of the coaches who had this need for training what he called rapid cognition, because he'd been working like the world's best football players day in, day out. And he had this epiphany that really what made the truly best players in the world truly special was just the speed of processing their brain and the way they could operate. So he knew what needed to be trained, but he didn't have any solutions on how to train it. So he just basically gave me the task of go out and find something that we can train rapid cognition with. I did a lot of research, contacted a lot of companies, and then I just came across Professor Faubert's research at the Faubert Lab with NeuroTracker, I should probably explain what it is first. So NeuroTracker is what's called 3D multiple object tracking. And it actually looks pretty simple, actually. So you'll see a big display, you wear some 3D glasses or wear a 3D VR headset, and then you'll have a bunch of spheres on the screen. Multiple of them will be highlighted for sort of the upper limit, and then they'll all move for about 8 seconds and mix up, and they'll bounce around in 3D space, and then they'll stop. And then you have to highlight the ones that you were told to follow to track, which is actually a surprisingly complex task. So in this task, you have to spread your attention. You can't follow the targets with your eyes. You have to do it sort of with your mental resources. So you have to divide your attention to 4 separate targets, like 4 separate attentional streams, 4 tasks simultaneously. You have to do it across a wide field of view. When you have a wide field of view, the peripheral visual networks in the brain light up, and you get a greater activation of neurons. And you have to do it by spreading your attention, not actually moving your eyes. You're actually doing tracking by increasing the processing that your brain does in different parts of the visual field. So you're sort of using attentional flexibility in some way. And then the last thing is that with the 3D component, which is the sort of ability to perceive depth from a different perspective in each eye, we actually task people with doing the task at different speeds. So this is the critical bit, is called what we call speed thresholds. So the task itself takes about 6 minutes, and it's comprised of sort of 20 mini tests that are each sort of 8 seconds of tracking. And at the end of 8 seconds tracking, if you get all your targets correct, then the next mini test will speed up. If you get it correct again, it will speed up exponentially, so it's logarithmic. And the algorithm works by basically finding the upper limits of somebody's sort of tracking speed threshold within about 60 seconds usually. And then once it sort of finds it, it narrows in and it tests them just above and just below sort of their breaking point. So they'll sort of succeed and fail 50% of the time. And at the end of the 20-minute test, after 6 minutes, we have a surprisingly useful measure of sort of high-level cognitive resources involved with this task. So we get this sort of unique window into the brain. And also with this sort of stimulation, because it's a threshold, we get an optimal learning effect. And typically we see with about 3 hours of training, we see significant transfer to improve functions across the brain and fast transfer to sort of real world performance. So that's the sort of the gist of the technology in a nutshell. So that is what I actually discovered and introduced to Manchester United. They really liked it. They sent a coach over to the Faubert Lab to investigate, and they asked him to come and present at Manchester United. I got involved at that time, helped present it to the club, and then the company founded, maybe partly sparked by the interest of the big sports club, biggest sports team in the world at the time. And then the company founded, and then we started a collaboration with Manchester United. I moved back to Manchester and worked with the club for about 3 months. And that's kind of how the company began.
Yeah, that sounds like such an interesting journey. And I'm also super interested in the technology and the research behind NeuroTracker. And it sounds like you guys are getting a lot of information about these participants that are going through the process and being able to feed that information back to them for allowing them to do better cognitive training. And then that's such an interesting way to light up lots of different areas of the brain besides for the visual area by bringing things into 3D and making them use the peripherals and focusing on multiple things at once. So I'm super interested in the story behind NeuroTracker and super excited to learn more. And before we dive in any further on NeuroTracker, I was wondering what sparked your initial interest and involvement in the neurotechnology or neuroscience space?
I've just always been a science geek generally, and also technologies generally. So it was just a natural fit. I was I started off in sports science and then went a different path, working in different countries around the world, just doing different stuff. And then this kind of came up. I was doing occasional sports science consulting at Manchester United, and it just came up and it just seemed a really good fit. So actually, so when we founded the company Manchester United, we only had the lab-based software, which had all these problems. It wasn't really fit for commercial use. So I moved to Montreal, actually moved into the CEO's house for like a month. So I went to Montreal for a couple of months, there were a few different people, and we assembled a small team, and we just built the sort of full sort of commercial product from scratch within 2 months, and went back to the club and said, here's what we got. And they were just blown away that we just, it's like whole software. But from that point, that's what got me really fascinated, is just kind of understanding the science behind it, how we can work it into technology and deliver it, and the different methods we can use. So, for example, like in the first year, I came up with a project. If you remember the Microsoft Kinect, it was a big buzz at the time because it kind of used visual cameras to do tracking. So I actually came up with a project to adapt that to actually do it with NeuroTracker and on a 3D projector, so it's sort of life size. And we did things like soccer balls flying out in 3D. But we used Kinect motion tracking to actually be able to detect where your hands are and do like goalkeeper saves. And if you got in the correct position in 3D space, the ball would bounce back with a sound and actually felt like it was in your hands. So I believe that was actually the first application of VR with 3D and motion tracking, so you could actually interact physically with the 3D world. There was the Wii, but that wasn't in 3D, so that was sort of about around the same time I started to use motion tracking. So yeah, so that kind of got me hooked. I found all the science fascinating, and actually the journey has been kind of even more fascinating because, like you said, so basically it's been sort of two-track within the commercial development of the company, and then there's just been the research, which has taken its own natural path, and the research has been fascinating. It's told lots of things about it. And then in between the two, we have lots of partnerships, sort of industry validation with all sorts of institutes. So yeah, so in the beginning, we were quite conservative in terms of the benefits. There was some really nice initial research on, people who were seniors who'd lost or sort of got cognitive deficits, and within 3 hours of training, they could be at the level of young adults, which was compelling. But we kind of I personally looked a little bit more like from the visual perspective, that it's really just making search strategy more efficient, more self-aware. But actually, the research itself unfolded that actually it's far more significant, the sort of nature of this task. So it's a very isolated task, so it's sort of tagged in certain systems within the visual cortex. But actually, because these are so significant, particularly 3D, because that's like the heavy lifting for the visual centers, it actually gets a lot of different systems to sort of integrate within the brain, which has been shown in qEEG research. So for example, the frontal lobes light up and we see sustained improvements in brainwave frequencies. And in some areas of the brain, we actually see similar effects to taking Ritalin just from watching balls bounce around the screen. If you do it in the correct way with the precise sort of stimulation, the brain seems to be very efficient at responding to this task. And also, as well as sort of broad transfer, so high-level cognitive functions, we see improvements in executive function, working memory, even auditory processing. We also see sort of improvements beyond the brain or towards the central nervous system, where we see improvements in reaction times. And also, like just last year, there was a study done by General Mexer Hospital with elderly patients with dementia and mild cognitive impairment. And just a 90-minute training intervention produced significant improvements in fine motor skills on 3 different tasks. So that's actually kind of shows you the power of the brain, essentially. If it gets the right stimulation, it can just prove its efficiency. And actually, it also teaches us that actually even a sense through systems such as vision, it's integrated with lots of different other sensory modalities in quite complex ways. So if you influence one system, you can actually have benefits that spill out across different systems. And then sort of on the industry side, some of the things that have been sort of discovered have even just been haphazard. So with this training technique, we have a recommended methodology of sitting down. So we do isolated training, so you're not distracted, keep it as simple as possible, so you 100% you focus on the task. So we work with a number of sort of world-class sports teams in the first year or two of commercial operations, and we gathered data with them. Professor Aubert published it as a study that got featured on nature.com's homepage and got a lot of attention around the world. But one of the things that came out of it was that 4 professional sports teams, one of the teams did the training standing up from the very beginning. All the other teams are sat down. And the difference is their scores were significantly lower and their improvement on the task was much lower. So this actually kind of raised a flag of questions, and later research actually showed that actually the brain needs to be sort of doing this task in an isolated way, and then you will get increases in neuroplasticity. And then within about 2 to 3 hours of distributed training, maybe over a few weeks, then it's ready to do more complex stuff. So then if you start standing up, you can manage standing up better. And then this led us to what we call a dual task training paradigm. So what you do is you do separate tasks at the same time as doing the NeuroTracker task. And if you build those up gradually, so they become progressively more difficult, then the brain adapts really efficiently to the point where you can do extremely complex things while doing NeuroTracker at the same time and still perform a NeuroTracker at a sort of maximum level. So the most complex example I can give is actually flying a jet plane while doing NeuroTracker and doing barrel rolls. That was a project that was done. Yes. So with training, the brain can be really responsive, but it's about finding the right sort of stimulation.
Yeah, that really is fascinating research. And it's also really exciting that based on what you've mentioned today, it seems like it can be useful for just about anybody, all the way from dementia patients to professional athletes, even pilots of jets. It's just quite interesting how plastic the brain can be, and it's really exciting to learn from you here that there's specific targeted ways that we can train it to be more plastic and to be stronger, for lack of a better term. And I did have a couple follow-up questions there. And so you mentioned certain areas of the brain lighting up, and so I was wondering what sorts of technologies you guys were using to image the brain or track the brain waves and see what areas of the brain are lighting up.
Yeah, this key technology used today has been qEEG, which it's quite different from EEG. EEG is, a lot more simple data. qEEG is a massive amount of data, and you get a lot more detailed activity of brain waves. So, I mean, we'd like to do studies like MRI and stuff like that, and we're in talks with some researchers, but it's still, still not perfect if you're in an MRI machine and you've got all this noise going on and can you actually see the screen and stuff. So there's limitations, but the qEEG findings have been really significant. Just the fact that you're stimulating the visual cortex at the back of the brain, so that's the only sensory stimulation going on. We see the frontal lobe light up, and also, in synchrony with that, and these are sustained changes, so these have lasted for at least 5 weeks. It's a 3-hour training intervention. These brain waves are heightened for a substantial amount of time, perhaps much longer. Along with that, we've seen studies that have also looked at, say, for example, decision-making in soccer, and actually the same sort of intervention, 3 hours of training, that produce what we call far transfer effects. So NeuroTracker's an abstract visual watching balls bounce around the screen. Playing soccer and making decisions on a soccer field is really very different. So that's what we call far transfer or long-range transfer. And what we see is an effect, so actually a significant, about a 40% reduction of passive decision-making errors that was sort of objectively assessed by coaches watching video replays who were blind to who was actively trained and who was passive and non-trained. Yeah, so it's kind of bewildering the fact that, just the right kind of visual stimulation can actually improve your capacity, for example, in your high level or executive functions to make complex decisions under pressure. Yeah, it's one of the sort of key findings.
I totally see some of the limitations that you mentioned in terms of the fMRI analysis. Like, for example, from what I understand, most fMRI scans are done while people are laying down. And I know you mentioned it's best to set up during the first trials of this or during the first couple of weeks. So definitely another limitation. But yeah, super excited to read that future research if it is to end up coming out. Another thing that really caught my interest is your initial founding of the company where you guys had built the version that had the 3D soccer balls coming out. And that sounds like a really interesting and creative way to transfer the technology into a format that's much more suited for a soccer team. I was wondering if you could talk a little bit more about those 3 months where you moved to Montreal and worked really hard on transferring the technology from something that's in a lab to something that you could bring out into industry and partner with teams like Manchester and others. If you can just tell us more about those few
Yeah,
months and
yeah.
what it was like.
Sorry, so yeah, from the technology
Oh yeah.
standpoint, quite interesting. So actually it led to us learning a little bit more about the science. So one of the things we found with the Connect, I mean, we commercialized it, sold as a product, lots of clients loved it, they used it extensively for many years until the Connect got discontinued. And now we're looking at using VR headsets because they've got really sophisticated tracking systems. But yeah, so our office is actually based right next to the university on purpose. So we work with the lab and discuss with the inventor, Professor Aubert, as we develop stuff and get feedback. But one of the things that came out of the Connect when we tried to do things like the soccer ball coming out, there was a little bit of lag, if it's not quite perfect, when you actually talk about training sort of real world performance, world-class athletes or high-level military, there's this risk of what we can call false learning. So if you're providing the simulation isn't very, very accurate, it has slight inaccuracies, then training with those inaccuracies can lead to inaccuracies in your real world performance. So that's where we sort of learn the sensitivity and also the importance of keeping the task very isolated. So we have a black background, we have a very small sort of cube as a frame reference, and then just the spheres moving around. And we've wanted to do lots of different things with it, but for the most part, we've stuck to the scientific principle of making sure we keep it pure and isolated training. However, there are different ways we can do physical dual tasks. You can do lots of different specific skills. But there are other ways we can do it without introducing the false learning. We keep things at sort of more generic level. So we have things like avoiding certain beams coming out was one type of dual task. And we've just been building in recently the ability to do things like the Stroop test with voice activate. I don't even know the Stroop test. If you see a word, then you have to say the color of the word, not the word. It's a famous test in psychology. So integrating that. So there's lots of tasks we actually can integrate into the virtual environment, but we learn that we have to be extra careful when we actually take a simulation route, because if you simulate reality, you've got to get very close when you talk about training effects. This is actually going to be a really big issue for VR because it's growing exponentially. Lots of applications already been used in the military. They've bought HoloLens and stuff like that. But it's very sensitive to making sure if the simulation is precisely representing what the task you're training. And in fact, on that point, one of the interesting research projects, when I mentioned the barrel rolls in the jet planes, that was actually a research project to test if airplane simulators, which are really advanced, really expensive systems, very, very sophisticated, if they actually represent what it's like to sort of do, fly a real jet plane. So one of the things that they theorized, the instructors, was that when the pilots get into the jet planes, they have a massive reduction in their cognitive capacities just because of the forces and the demands and the stresses, which they don't get in the simulators. So they wanted to look for evidence to see if that was the case. So what they did is they integrated NeuroTracker into the dashboard of the simulator cockpit and the real jet plane cockpit, and they tasked the pilots with doing sort of simultaneously while looking out, sort of doing it as a peripheral task, and then measured the speed threshold difference between the simulator and the real live jet flight at different levels of flight maneuvers, and the most difficult one being barrel rolls. And it showed very clearly actually that at lower levels with simple maneuvers, the simulator was pretty close to real world sort of jet flight. But once it got to complex maneuvers in the simulator, there wasn't much loss of cognitive capacity, but in the jet plane, there was a huge loss of cognitive. All their concentration had to be on flying the jet plane. So it's kind of an example of the simulator is great, even though it's done to a really cutting edge, but it's not the whole picture when it comes to sort of real world performance. So yeah, generally with VR and neurotechnologies, whenever there's simulation involved from a sort of neuroscience and psychophysics perspective, which is sort of understanding how the brain processes sensory reality, there's nuances that the brain actually finds are very important, and it will learn from things that you don't necessarily want it to learn from. So that's part of the process we've been through in terms of keeping the stimulation pure and not introducing biases or perceptual noise.
That's such an interesting thing that you guys found out there, and agreed, you don't want to see that false learning. So that's a pretty cool discovery, and also it seems like it would be quite useful in just making sure you're building the best system possible. And so the next question I had is, what is NeuroTracker working on at present?
Yeah, so we're looking to integrate with the Quest 3, and also kind of interesting actually with the dual task training paradigm is I've got a pair myself of some of the latest AR glasses, which have been waiting for. I knew they were, I've been following AR for many years now, and I knew clearly it was a long way off, and it's just about come to fruition now. We've actually got really high quality displays on low cost, very lightweight devices. There's only a few models on the market at a pretty good standard. But they give you an exceptional experience of basically like a small home cinema screen. The lenses they've used actually, even though it's only like 1080p each eye, it actually feels a bit more like 4K because they've processed the sort of reflected vision thing, and actually produces a really, really nice, crisp, clean experience just with a lightweight pair of glasses. But the interesting thing is that you can kind of adjust the glasses to be see-through. With NeuroTracker, we have a black background, and if something's black in AR, it goes straight through it, less lighting from the outside world. So what you can do is actually track the targets with NeuroTracker wearing the AR glasses, as well as seeing the real world at the same time. So you're basically overlaying. It's not full VR, it's only very basic AR at this stage. The full VR will probably be like, say, this year or early next year. But at this stage, right now, you can actually, do, for example, NeuroTracker, virtual elements moving while looking at the real world, which is pretty cool because then it opens up the flexibility and it removes that simulation problem I mentioned, that you could actually just do real. So, for example, a soccer player wants to practice doing his multiple object tracking at the same time as doing soccer passes. Then you can do that with a pair of AR glasses and from a phone, so you can actually do it and move around, and you can actually see the real world, do real skills. There's no noise or pollution in the task. He's doing perfect training while having the added load of doing NeuroTracker overlaid on top of it, and that is quite exciting. So that's the development we're looking at. And fortunately, there's not a lot of development work. It's just more integrated, make sure it fits, and we don't have too much movement in the screen, and just fine-tuning the technology. Another area we're looking at is integrating what we call closed feedback, loop feedback EEG. So some of the research at the Faubert lab was really interesting, as in they found that with the NeuroTrack test, when you're tracking your targets, it has a particularly strong sort of effect on eliciting alpha peak waves. But when you lose the targets, you see a sudden change in brain waves. So normally, most of our clients, they'll, be in rehab centers or fitness centers, performance institutes, and they'll have a trainer sort of often supervising the people doing the training. But they don't know what's going on inside their brain when they're doing the tracking. They could have lost it. They could be perfectly tracking. But with fairly affordable EEG devices now, you can get just a sort of peak wave measure, and you can reliably see when somebody's lost tracking just from their change in their brain waves. So at the Faubert lab, they introduced a closed loop feedback system so that when they detected that loss of tracking, the software automatically re-indexed it, sort of flashed or highlighted the balls, and then so they could actually carry on doing tracking. So instead of doing 20 mini tests where we present the targets, they move for 8 seconds, stop, you identify them, you get the answers as feedback, and then you go on to the next one. They could just do continual movement. So you're just doing continual tracking. And they did a study of that, they published, and they found with that technique where the sort of, you're modulating the difficulty of the task, or the sort of the feedback from the task with tied to brainwaves, that even though NeuroTracker is really efficient, takes about 3 hours to get really nice near and far transfer effects, that time reduced to about 90 minutes. So it made the training about twice as efficient. So that's something we're really looking to develop on. Yeah, and another sort of area that might be interesting, and we never mentioned this public before, so you can have this as an exclusive if you like. It's one of our other technologies we've been keeping in the background for a little bit until the other technologies are ready to support it, and it's called NeuroTuner. So the science is very esoteric. It involves the sort of more like a systems science look at the brain. It involves principles known as sort of stochastic resonance. So the best way I can put it is maybe, like studies with endurance athletes show that, they run to their maximum capacity when they feel they're completely depleted of energy. If you give them some sweet water that has no calories in it, the brain thinks it's getting sugar, suddenly unlocks a reserve, and then they can start running again and perform, even though they've run to complete exhaustion. The brain operates in a similar sort of way because it's very energy hungry and it needs to be an efficient system. So it's not operating at bandwidth. So maybe even fight or flight moments or near-death moments, or emergencies when people say time slowed down, and so the brain sort of then using its sort of expanding its resources or its capacity to actually process more information more intensely. And it turns out there's actually a natural way to do this through the frequencies of sensory stimulation. They're in a particular sort of noise pattern that's undulating. The brain's sort of trying to figure out patterns. Always, it's a pattern recognition machine. If it's sensing something that doesn't quite make sense, it sort of kicks up its gear to work a bit harder, say, what's going on here? And it turns out you can actually, from the studies that have been done, these have been studies that have been published over maybe 7 to 8 years, we really effectively showed that actually it can be any sensory stimulation, by the way, but it could be visual, but auditory is the most practical. So for example, you put some headphones on, you put the right stimulation in, and the right stimulation is different for different people and different at different times of the day or week. But what we do is when we modulate the stimulation of this sort of sensory frequency, then we measure skin temperature changes. We can use HRV and other modalities, but when we get close to the zone where it's giving optimal stimulation, we see a significant increase in temperature as a response. And we can use lots of devices, but when we see that, then we say, okay, we get in the zone. It's like a hot and cold approach, and we will use an automatic process to get the sensory stimulation at the correct optimal level for the individual at that moment. And once they do, it's a little bit like spider senses, I guess. So all sensory processing bandwidth is increased, so you see things in more detail. So we think we see things as raw reality into psychophysics here, but actually our brain constructs a model of reality. So it takes all the sense information. So for example, with vision, we get light in the retina. There's some filtering the level of neurons in the retina that separate and categorize the information that's receiving. It's like colors, shapes, or motion. And then different parts of the visual cortex, the subsystems, analyze it, interpret it, and then the whole visual cortex then builds it back together and says, this is our visual model of reality. So in that process, you're actually trying to sort of discover essentially what's going on. And when you actually stimulate that system, it can work at a sort of higher threshold. So that means more of the information that's coming in is being processed instead of being filtered out. So when you have an increase in the information that you're actually capable of processing, you're experiencing reality at a higher resolution. And it's not actually just sensory processing. There's lots of interesting research around this space to say it improves higher order cognitive functions like creativity, and also it stimulates the central nervous system. So there's interesting research showing it improves rehabilitation in stroke patients, and even with animals. So this is a stochastic resonance of the universal system into our biological systems. So yeah, that's our next technology. Will be a closed feedback loop system that can automatically zone you into sort of a neurotune state, and then what you do when you're in neurotune state, maybe you experience things at a higher level. So maybe music appreciation is one thing, but what we think is the most valid thing is actually to do something that's actually involved in training. So if you actually want to get better at something, you get into a neurotune state where your brain central nervous system can process more information more efficiently, and then actually get more benefits from that training. A NeuroTracker is a perfect candidate. So, that's straight away, those two go together. We'll get into the neurotune state and then do NeuroTracker training and get an increased response from it. And there's already a study that was kind of published with the American football players using this type of approach, and we saw an increase in their learning rates from this sort of noise stimulation that was done auditorily. So yeah, so that's one of the ones we're hoping to commercialize this year, but nobody knows about it yet.
I appreciate you sharing this new technology that you guys are working on with us, and I'm super fascinated by it and I'm super excited by it. I guess a quick follow-up question to the recent technology that you just explained is the training while you're in this, I believe you called it neurotune state. Is it basically training while in that state? Is that helping optimizing the performance of that person only when they're in that state, or does it help? Does it help it both when they're in that state and when they're just at their normal baseline state?
It'd be nice if it was sustained, but it's like a turned on and turned off. So it's kind of like, here's the stimulation. Okay, I've got a high frequency, increased resources being used by the brain. So it's kind of like, okay, now it's important. I've got to step up my resources for the body and the brain. And then when you stop it, you'll get a drop off. Yeah. But
Yeah.
well, it can be sustained for a while, but it's not like you get benefits for a day or two, you know. So what we do, it's partly theoretical at the moment. So the principles have been really, really well studied, the effects and the sensory systems and stuff like that. But what we haven't got to, because we haven't released it commercially, is the sort of real world effect. So that's the bit that's going to be exciting. So, you know, lots of our partners and clients and things can actually start to use it, and then we'll get indications. And luckily with our company, we get the feedback that we get from industry often that leads to discoveries that guide future neuroscience research. It goes both ways. And in this case, that's what we'll be looking for, to see what our, you know, trusted clients and experts report. We have lots of people, you know, really in all different domains. It could be esports, Formula One, you know, military, professional sports, and rehab, and, you know, concussion management, and all sorts. So there's so many different applications. So we'll actually get feedback from all these different industries. And then we'll see things that are interest, maybe do a few case studies here and there, collect that, and then that can be something that actually guides research, maybe primarily at Fovear Lab, but we collaborate with lots and lots of different research institutes around it. Part of my role is to provide consultancy on the best practice of how to use NeuroTracker and share findings from other research institutes, because there's about 135 published studies today, all of which have been completely independent and no commercial funding whatsoever. It's just pure science approach to say, okay, NeuroTracker findings look interesting. What if we explore it in this way? What if we apply it to this population? What if we, you know, look at dual tasks? So that's kind of how it's grown. So yeah, that would be the approach at the moment. It's hypothetical. We understand the principles. We know that it works. How it applies to sort of real world benefits, lost to discover. That will be the beginning of the journey.
Yeah, and it seems like, as you mentioned, there's a really symbiotic relationship going on between academia and industry, and kind of they're feeding off of each other and learning things from each other. So that's super exciting to hear about. And I'm also really looking forward to just reading more about new technology that you guys are building, and the future research that gets done on it.
Yeah, if you want to look at the papers, they're very technical and there's quantum physics principles involved, but Eduardo Lugo and Jocelyn Faubert, if you just type, you can probably just type stochastic resonance, but technically they term the NeuroTuner state as the fulcrum principle, almost like leveraging a pivot, so you get the optimal effect. So fulcrum principle, Faubert and Lugo, those terms, you'll see the papers. Yeah, I think there's about 11 papers that we published today.
Yeah, sounds good. And I'm looking forward to giving them a read. And so my next question was, and we kind of touched on this a little bit already, but if you're able to go into a little bit further depth, what have you learned from your partnerships with the professional sports teams, NASA, the Air Force, etc.? And, you know, just to the extent that you're allowed to talk about it, because I know sometimes these things may be classified.
Sports teams tends to be quite sensitive, so that they're the ones that but yeah, the United States Air Force, that's something that's relatively public. They did kind of an inside study, so I can't share the findings of that because they didn't make it public. But yeah, so that was a project. So they had a pretty cool initiative called Pilot Training Next. So they had a problem essentially, as in, you know, Top Guns, there's just not enough pilots for the demand for the Air Force. And it takes too long to train them, and it's too expensive to train them. So they need solutions to make the training much shorter. So they proposed going from a 12-month training program to a 6-month training program. For that, they needed innovative emergent technologies. So they held a competition. I think maybe 300 or so companies entered, and NeuroTracker was the only one that was actually picked to actually be part of the actual training program. So we entered into a collaboration with the Air Force, and all the sort of trainee pilots, they all went through a NeuroTracker baseline and did NeuroTracker training throughout their program. And at the end of the program, they successfully graduated, most of them at the same graduation rate within 6 months compared to 12 months, which is quite an achievement. But there was a lot of interesting things that kind of happened along the way. So like at the very beginning, one of the concerns was that actually the trainee pilots work in memory tests, because all sorts of batteries, neuropsych batteries and assessments done with them, were really quite low compared to the instructor's levels. So there was concerns, because obviously working memory is really essential skill in this sort of high level demand task. And actually through the training, as we saw the NeuroTracker learning rates improve, then they reassessed on the working memory measures, and I'm not sure exactly the time frame. Then the next assessment, their working memory measures were actually higher than the instructors, or on par. That was the first initial finding. We seen a deficit and we've seen to recover it. So if your working memory was low throughout the whole training program, that would probably mean you'd have much less success. Another area which is really, so I didn't really touch on this, but so with NeuroTracker, we see really nice learning curves with all sorts of different populations, even kids with really severe intellectual difficulties. They can do this task and improve on it. And we see what we call nice learning curve trajectory, as in you'll do your first 6-minute session, you might get a score of 1.0, which is like the actual speed that the ball's moving in sort of real world terms. And then after your 30th session, you might be at 1.5 or higher than that. So that sort of 50% improvement is kind of approximately what we see with a lot of populations over 3 hours of distributed training. It's really significant because this task is so simple. There's no technique or practice related effects. If you do this task, you'll learn how to do it in 60 seconds, no problem. Everybody does. And then nobody can help you how to do it better. So if you improve at the task, it's just because your neural efficiency is improved. So that gives us sort of measures, kind of like a representation of functional neuroplasticity. So as we improve from session to session, we see this sort of natural fit at different trajectories. And that trajectory of that learning curve tells us something really important about the brains of different populations and different people. So for example, there's one famous study that was published in Nature that actually showed that the world's best athletes have sort of hyperplastic brains and their learning curves kind of go through the roof compared to like healthy university students who don't play sports. They're just way superior. Whereas, you know, kind of like an abstract intelligence task, most people before the research might have assumed that university student would fare better than athletes because they're not deemed to be intelligent. So yeah, so you get this nice sort of learning curve. And that learning curve, we found lots of really fascinating things. It's kind of like a function of neuroplasticity or a representation of it. And the lower it is, so for example, if you suffer the effects from cognitive impairment like concussion, your learning curve is going to be very flat. You're really going to struggle to improve, or it's going to be high. And in the pilot training next study, at the end of the 6 months, we had the learning curve trajectories, and there was 3 groups, which was 1, the top guns that became the fighter pilots, 2, the less skilled trainees that actually became sort of heavy aircraft pilots with multiple crew members, and then 3, the ones that didn't graduate. So we actually mapped their average learning trajectories for the 3 groups, and it produced a beautiful correlation where the top guns were these really high learning curves, the heavy aircrafts were sort of mid, and the dropouts were low. So effectively, if you'd have done, you know, it's partly hypothetical, but effectively at the beginning of the program, if you'd actually done 3 hours of NeuroTracker training and measured these learning curves, say over 1 week, then you could have probably predicted who would succeed and who would fail. And sort of relating to this is a trader study that was done last year with real traders doing stock market trading. So I think it's about 40 traders, and it was over something like 3 months. They did 1 NeuroTracker session a day. The purpose of the study was to see if that single 6-minute measure, the speed threshold, would correlate with their trading performance on 10 different metrics. So they actually took that measure. So at the end of the study, they found really beautiful correlations with all 10 metrics. But the more interesting finding was sort of anecdotal. Because they did 1 session per workday, they got really nice learning responses. But actually, when you looked at the learning responses, it predicted who would be the most profitable traders. So you can imagine in sort of talent recruitment, identifying potential leaders, or in the business world, sports world, or whatever. And we have an interesting project, it's not completed yet. So we went to the NHL and NFL combines and got lots of data. Only not learning curves though, which are much more powerful, but just single sort of baselines. And we have all that data we're sitting on from about 9 years ago, and we're planning to do like a 10-year longitudinal study to see if those single measures, 6-minute measures, correlate with where the athletes are in the professional sports world now that they make it and it becomes a success. So yeah, so you get all these interesting insights. So the pilot training next is a really nice example. And the fact that it was so successful, they actually spread it into what they call the Army Training Next ATM programs. Yeah, and also in that, they kind of did an interesting application of the dual task training paradigm, where they actually had to, you know, so pilots have to handle audio feeds, and that's actually quite attentionally demanding. So different sensory systems, lots of complex information involving language. Trying to do that while you manage an aircraft and you're already maximum, that's a really extreme sort of form of multitasking. So we actually did that with NeuroTracker. So the NeuroTracker task kind of became the simulation of the cognitive overload of the mental task of flying a jet plane, and then they had to listen to radio cues, and then you have to identify them in the NeuroTracker task with a little special module. We've done things like that for other groups. So we did another one for special forces for sort of what are called close quarter battles, where it's kind of room clearing. Imagine, clearing terrorist out of a building, then in that situation, even like elite special forces, they have an atrocious casualty rate because it's extremely dangerous, extremely unpredictable. There can be explosives, things like that. So the special forces were looking at solutions to sort of reduce those risks. So they actually did NeuroTracker, and they did a dual task training paradigm, things like weapon handling skills at the same time. And they assessed them on their really, really advanced simulations before and after, and they found a reduction in casualty rate by doing the sort of dual task integrated paradigm. So yeah, so those are examples. There's lots more, but examples where we actually learn from industry, and there's this beautiful sort of coupling where it actually influences neuroscience because, over the years, occasionally we have sort of group discussions. So like we held a summit for lots of different sort of sports teams, world best sports teams. So that's sports scientists and doctors and stuff to come together and discuss what they found with using NeuroTracker and how they applied it. So for example, there's like a rugby team in France that actually used NeuroTracker to predict the impact of playing an actual rugby game, which is a lot of physical damage, and then use sort of biomarkers, blood-based biomarkers to try and measure. But they actually found that drops in NeuroTracker scores correlated with the biomarkers, so they could actually just use the 6-minute NeuroTracker session to essentially get a picture of what damage is done with somebody, and also they use it to deem when they're ready to recover and ready to go back into training. So yeah, there's all sorts of stuff like that. It sort of really influences. In fact, there was a cool study done again in France with rugby players actually looking at the effects of fatigue. So if you know sort of team sports, you'll know that pretty much most outcomes are determined by errors or mistakes in the second half of the game when people are really getting fatigued and their concentration levels lapse. It's not that their performance improves. So they looked to see if they could minimize that impact. So they took like elite rugby players, they put them on an exercise bike for an hour and put them close to their VO2 max at very high levels, got them really exhausted, and then tested them on NeuroTracker while doing the actual, the physical exercise at the same time as doing a NeuroTracker test. What they did is they took one group who'd never done NeuroTracker and took one group who'd done a sort of pre-training, so they're already pre-trained, a bit more established at the task. And then the difference was in the group that was untrained on NeuroTracker, when they tried to do the task on the exercise bike, when they're absolutely exhausted, they had about a 35% drop in their NeuroTracker capacity compared to their initial baseline before the exercise. A significant loss of complex awareness and visual processing. Whereas the pre-trained group were very resilient, and they only had about 1% loss. They maintained their ability, their situational awareness ability, by about 98%, the same as what they would have done if they weren't fatigued. And that was only a 3-hour intervention. So you can imagine, if you actually just look at it from, reducing the effects of fatigue on cognition, it's already significant just in that. But yeah, that's an example of working with professional teams of what they come up with their problems, and then collaborating, researchers getting together and thinking that could be interesting, deciding to do a research study with them. Yeah, I personally, I think the best findings are when you actually get, problems in industry and you have researchers who collaborate with them to actually investigate them. Yeah. And some interesting findings in esports as well, actually, recently. So like in esports, one of the problems is esports athletes typically train like, up to 14 hours a day. They have terrible diets and really poor sleep. So there's a university in Texas I wanted to study to see, what are the effects of, sleep quality and diet quality on cognitive functions. So they use NeuroTracker as the measure. And there's other studies showing NeuroTracker related to esports performance. So they knew it was a relevant task. But yeah, in that study, again, with the learning trajectories, they actually found that if their protein intake was, insufficient under the recommended guidelines, then their learning curves were much flatter, as in they had reduced neuroplasticity. I believe this is the first time it's sort of been discovered from a functional perspective. So you can imagine if you're dedicating your life and they have a high burnout rate, esports athletes usually only last about 4 years and maybe retire at 23, 24. And you can imagine you put in 14 hours a day, to do the best you can and get as much money as you can in that short career window, but not eating sufficient protein, and you're not going to be actually responding to the training that you're trying to actually use to get yourself better just because you dieted. And there's some other examples of really interesting diet effects that NeuroTrackers sort of revealed. So yeah, so that sort of industry and research combination, it's a one-bell combo. So I really wish there was more of it about,
You're getting tons of useful data and correlations and lessons learned from your partnerships with the industry and military, sports teams, esports teams. And wow, I was quite fascinated by basically all of the situations that you talked through right there. And this is a good transfer into my next question. A little bit during your response there, you were talking about how the system, the actual task that is being trained during NeuroTracker is such a simple task that you'll learn it really quickly. And then you can't get training from somebody else on how to do it. And it helps to isolate the neural improvements as you're improving on the task. And so my next question was, when you're like delivering this NeuroTracker product to people across different domains, are they all getting the same activity fed to them, or does it need to be customized, like a different version for military versus the stock traders versus the athletes, for example?
Yeah, there's two answers to that question. There's kind of a no and a yes. So a no as in pretty much all the researchers use what we call the core session in NeuroTracker. There's different sessions that work different attentional systems slightly differently, all based around the same approach. And that we see just seems to be universal. In all the 135 studies now, there's really significant assessment effects, or it seems to produce really nice transfer effects, which is kind of, it's surprising considering the diversity of the population studied, everything from dyslexia to autism and all sorts of conditions to super high levels of human performance. So yeah, so the findings seem to be fairly generic. However, when I mentioned that dual task training paradigm, that's when we can, one, extend the benefits beyond just doing the normal training. So what we see is you'll get improvement. It starts to level up over time. You keep improving, even 400, 600 sessions in the data, we see people still improving, but it gets smaller and smaller. However, if you introduce these progressively more complex dual tasks in the correct protocol, then you get a boost in that sort of improvement over time. So you can sustain it or engage it. And it's also more interesting because it can get a little bit monotonous watching, the same ball bounce around the screen day in, day out. So yeah, but it also allows us to get it skill specific because it's very flexible what tasks you do. You also have the restriction now to be able to see the screen, whether it's wearing, with AR glasses, headsets, or projector, or doing it, running from your phone, screencasting to your TV. We have some adequate classes that actually work with normal 2D displays. So anybody can use the software pretty much anywhere, as long as they have a phone, they can run it to display and do the training. But yeah, in that sort of application with the dual task, because there's quite a lot of flexibility in all the different things you can do while doing NeuroTracker at the same time, that gives a lot of sort of freedom for experts to specialize, to say, I want you to do in this type of task while overloaded on NeuroTracker. And there's two kind of approaches to that. One is to, do NeuroTracker and add complexity and make it sort of richer and stimulate the brain in more ways. The other way is actually to look at the impacts of what these particular skills or tasks, what impacts do they have on NeuroTracker, which gives you a measure of how significant they are. I mentioned the jet plane, but like Professor Aubert did a pilot study, was kind of quite interesting with ACL injuries with athletes in three different sports. And basically you show that actually when they do certain jumping sequences, he did really sophisticated motion tracking, their movement skills was correct. Fine. However, when they did NeuroTracker at the same time, which kind of like simulating the situational awareness demands of sort of playing sports on the field, then their movement coordination changed because attention is a shared resource in the brain. So even the act of standing up draws some attention. And if, for example, as research showing, if you're walking down the street and somebody asks you to count down from 100 in 3s or 7s, then nearly everybody stops walking, just because walking is burning up the resources, the attention that the brain wants to use to doing the maths abilities. So yeah, so effectively what you can do is use NeuroTracker as a measure of what the impacts of certain tasks are. And if those impacts are really great or severe, then you know that that person is probably not ready to respond under pressure or perform under pressure. So it's used as sort of a risk assessment tool. Obviously, in military and sports, that's really significant. It's been used quite widely. You can do, you're in this sort of situation, are you going to be able to perform and do a prediction of it? But in the traders study example, the correlations are strong enough that actually if there was a drop in NeuroTracker scores on a certain day, it actually showed, with quite high confidence that that trader would lose money that day. So they could take the day off and they would actually be more profitable. So that's a kind of risk assessment you can do, and you can include that dual task training to put them under the pressure to make that assessment even more sensitive. So yeah, so it's kind of general and then high specific, and it's part of what we call a NeuroTracker learning system. It evolves over time. You have to start with the basic. As you progress, you can get more sophisticated and go in different ways. So most of our client base are actually performance or rehab or wellness centers that specialize in their own application of it. So it's managed.
Yeah, that makes sense. So, you kind of start with the baseline version, and then depending on the application, it may get more complicated from there. That makes a lot of sense. And, that also makes sense that could, as you mentioned, make things less monotonous, as well as potentially lead to some customized learnings or customized findings.
Quick note, it's just that physiological exercise or doing NeuroTracker, that's kind of a perfect combination because the brain, is functionally coupled with the body. And when you stimulate one, you stimulate the other. So that in particular is, for anybody who wanted to do NeuroTracker, that is a really nice application. Anything that really engages the brain, gets to, doing complex stuff at the same time as doing exercise is a, really good thing for healthy stimulation.
Yeah, absolutely. And that feels a little bit similar to what you mentioned about when people were walking and they like to stop and when they're counting backwards from 100. And, if you're exercising while doing NeuroTracker, it's kind of forcing you to use both of those systems at the same time. And I can definitely see that being useful. So for my next question, I wanted to zoom out a little bit and ask if you have any predictions for the field of neurotechnology over perhaps the next 20 years, and both from the perspective of the specific subset of the field that you and NeuroTracker are working in, and maybe even zoomed out a little bit more and looking at the whole field of neurotechnology at large.
Yeah, I'm a bit of a neuroscience geek, not specific to NeuroTracker, although there's lots of fascinating things in there. So yeah, I think 20 years, this is my take anyway, 20 years is kind of ambitious to even try to begin to predict. So I'm kind of not necessarily a fan, but I followed Kurzweil's work ever since his first book, I think in 1988, The Age of Intelligent Machines, and I think the next one was Spiritual Machines. But anyway, I followed that and I found it fascinating. And I've sort of followed just science and technology in general over the decades, looking for this exponential curve. I mean, sometimes it was really taking off and there's these surges. I mean, smartphones are one example, on the internet and stuff like that. Those things I've witnessed because I'm getting older now. But it's only been in the last year or two, maybe three, that things are really starting to what he terms as the knee of the curve sort of take off. So I actually think even the next 5 years could be quite unpredictable, as in there'll be technological innovations we wouldn't expect. And I'm very interested in just following those generally. But in terms of neurotech for human performance and wellness and stuff like that, there's lots of promising stuff going on. So generally, as one sort of box or field, you've got this sort of neural stimulation. So you've got low-level electrical currents, magnetic stimulation, all sorts of different methods. A lot of those have been around for a long time. It's actually only because now the research is getting sophisticated enough, and time machine learning analysis of the research data, that they're actually starting to learn that, okay, it's not a one shoe fits all, it's actually, you've got to apply in a very specific way for certain populations, respond differently, maybe at different times, and now starting to learn how to sort of use the correct technologies in a precise way that you actually get the desired benefits you want. A part of that's also coupled with actually just learning more about the brain. Higher resolution scan imaging, neuroimaging has got a lot more sophisticated. Even, AI is coming in actually. So for example, MRI, there's this really cool application of sort of AI actually increasing the resolution of just the same imaging technology to get vastly greater detail. So all that's kind of kicking in and all that's really, really taking off and increasing speed. And I really do see that. And I follow the research quite a lot. And I usually, LinkedIn, up and post on, sort of latest stuff that's going on. That's exciting, all sorts of different fields. For example, just at the end of last year, the first time quantum mechanics was used as a therapy to actually treat brain cancer. And this actually involved creating machines that were so tiny, they're called nano bioantenna, so tiny that they're actually sprayed onto the surface of tissue. And then they actually get into and attach to tumors and produce an electrical signal that actually causes quantum mechanical effects and causes electrons to get knocked off, and in turn that causes the cell to commit programmed cell death or apoptosis. And it's just fascinating. So they're actually utilizing quantum mechanical systems with, you know, this sort of space age technology that you spray on, like something out of a movie. And that's actually been demonstrated in scientific research. It'll take a long time for the clinical approval, but that's already like a significant application. So I can see a lot more sort of breakthroughs like that, with the sort of the technology is growing really, really quickly. The research is slower, but really, really important to understand how to apply it. And then you've also get AI and machine learning that can actually meld the two sort of areas and accelerate them. And that, I think, is a powerful sort of, you know, combination. And even in the next 2 years, I could see some things that will be, people will like, wow, we never expected that. Yeah, so I think it's going to be transformative. I think there'll be lots of applications that could be really, really powerful for just human wellness and human performance in general, and specifically to treat certain diseases and conditions. Yeah, lots of promising applications.
I totally agree with you there. I think it's really a transformative time ahead, and I think we're really seeing a perfect mix of updates and AI algorithms and technology, progress in the research, and then also just materials and technological innovation that are all happening at the same time. And I think once these things all start getting combined, I think there's lots of exciting things ahead. So I definitely agree with you there. And so my final question was, can our listeners contact you for further discussion after the episode? If so, which types of listeners should reach out to you? How should they reach out to you? And additionally, what sorts of topics should they reach out to you about?
I'm pretty open, to be honest. I've probably really got into using LinkedIn for the last year or so, but I've had maybe 100 conversations with all sorts of different fields, all really positive. So yeah, I'm open. So we can just find me on LinkedIn, just type in Lee Sidebottom. It's a fairly unique name, so it usually comes up straight away, and just reach out and just let me know what you're interested in. I'm more happy to discuss whatever. So generally, I'm more sort of focused on neurotech broadly, neuroscience and psychophysics, and a little bit on the sort of AI side. I don't have much expertise there, but I think it's really interesting. Yeah, so those areas, and then just generally more broadly sort of human performance and wellness, you know, so it's esports, sports, or Formula One, or whatever it is. Anywhere sort of human performance is sort of, even, you know, work with rodeo athletes and things like that. So in diverse areas, but anyways, it's sort of more extreme end of human performance spectrum, or human wellness or conditions recovery. Those are very interesting domains, yeah, for us as a company.
Yeah, well, sounds good. And thank you again for coming on. It's been super interesting to learn more about your story and about NeuroTracker's story.